Okay, so welcome back to our last talk of today. So now we're going to listen to Bryce Kerr from University
of New South Wales.
And he's going to speak on Kloosterman sums over lattices.
All right, thank you. So I'll start with three integers. Which satisfies some coprimality condition. And this bracket just means GCD. And I'll define the Kloosterman sums. And E is the complex exponential. And N bar is the multiplicative inverse of N mod Q. So these sums are named after Kloosterman, who introduced them in the early 1900s. In his refinement of the circle method. In particular, the use of Kloosterman sums in the circle method allowed him to handle binary quadratic forms in 4 variables, which was an important boundary of previous approaches. Now, to make use of these sums work in the circle method, Kloosterman needed a power-saving upper bound for these sums. And he showed that these sums are less than q to the 3 on 4. Now, note if you just bounded these trivially by the triangle inequality, you would get something of size about q. So this is telling us that there is some cancellation in the phases of this exponential. Now, his proof is very nice, short and elementary. And I'll sketch just the 2 ingredients. So it combines an evaluation of the 4th moment of these sums. With the fact that the Kloosterman sums are constant on lines through the origin. And one way to see that is just by making a change of variable in the defining sum. So since Kloosterman's work, there's been a lot of activity on these sums, and we now know sharp pointwise bounds. And what I'm about to state is often referred to as the Weil bound. With the same conditions on A, B, and Q. So we get square root cancellation, and this is exactly what you would expect if our phases in the exponential were randomly distributed. So I'll sketch the proof of this. We start with a prime factorization of Q. And apply the Chinese remainder theorem to summation over n. And this tells us that our Kloosterman sum factors as a product of Kloosterman sums to each prime power. Where these A tilde and B tilde might not be the same will depend on the specific prime we're taking a factor over. Now, if alpha I equals 1, a consequence of the Riemann hypothesis for function fields over finite fields, often referred to as the Weil bound. And if our exponent alpha is greater than 1, then we can use p-adic stationary phase. So I've written a redundant alpha I. Yeah. All right, so now we know bounds for each prime power, combining with the fact that a given integer doesn't have too many distinct primes dividing it. We can combine these two bounds to get our stated result. And this little o of 1 comes from the fact that Q might have many prime divisors. Now, estimates for Kloosterman sums are foundational to many parts of number theory. And I'll list a few. So one is subconvexity for L functions. Twisted moments of L functions. Which in particular lets you count zeros of zeta on the critical line through the method of mollifiers. And also the level of distribution of convolutions. So for this last point, you can think of this as, say, variations of the Bombieri-Vinogradov theorem. Now, for these sorts of applications, we don't directly encounter these complete Kloosterman sums. We encounter so-called incomplete Kloosterman sums. And by incomplete, I mean we're summing over an interval whose length might not equal the period of our function inside. So in particular, you can think of n being less than q. So it's not difficult to reduce incomplete sums to complete sums. To get the following bound, and this is through a Fourier expansion of the indicator function of an interval. So we'll take an approximation to our interval. Then you just Fourier expand our function 1. And then apply our bounds for complete sums. So improving this bound for a given A and Q remains an open problem, and it has been for some decades. And a conjecture due to Hooley. States that so note that we are off the expected bound here by a lack of dependence in the length of summation. Now, there hasn't been much progress on Hooley's conjecture except for specific types of moduli. Say, for example, if you're smooth, you can use what's known as the Q van der Corput method. And if your Q is, say, a large power of a small prime, you can use what's known as the p-adic van der Corput method. So wide open, yeah, wide open. So not even an improvement on this theorem I've stated is known. So say, for example, can you replace the half there with a half minus delta for a suitable range of n? So the situation isn't so bad because in most applications of Kloosterman sums, we encounter averages. And I'll refer to them as bilinear Kloosterman sums. So there are many variants of these bilinear Kloosterman sums, and I'll be talking about a specific type. So we sum integers in some dyadic interval. And these sorts of sums are usually split into two categories. The first is type 1 sums, and these are when our coefficients are 1 or the values of some smooth function. And the sharpest bounds for these sorts of sums are handled by spectral theory of automorphic forms. Now, type 2 sums defined as not type 1 sums. And these are when we have no information about the coefficients other than, say, L2 bounds or L infinity bounds. Depends on the lengths. Yeah. Yeah. Yeah, because the lengths are going to inform what techniques you use. So the focus of my talk will be on type 2 sums. And one of the first very strong bounds for these type 2 sums is due to Duke, Friedlander, and Ivanchik. In their paper, excellent paper, bilinear forms with Kloosterman fractions. Where they introduced or used something now known as the amplification method. And once they used the amplification method, their main input was just pointwise bounds for Kloosterman sums, plus the Weil bound. Now, the approach of Duke, Friedlander and Iwaniak's application of the amplification method has since been improved by Bedin and Chandy. By refining the application of the amplification method. But in the end, they still reduce to pointwise bounds for Kloosterman sums. So these are quite technical papers, so I won't say too much about what's involved in applying the amplification method, but I will state the sums we arrive at the second last step before we apply the Weil bound. And the situation is similar for both Duke, Friedlander, and Iwaniak, and Bedin and Chandy. So I will simplify the statement of these sums because even writing these down is quite technical. So we have three parameters, L, D, and capital N. And the sums we arrive to look like this, and the coefficient A might depend on our L's, but in a very mild way. All right, so then the last step, similar in both papers, is we expand this congruence condition. So for example, we might write L1n equals L2n plus m times d, and make a change of variable for n1. And this will give us, for fixed variables in the outer summation, something like so our sum still has the same shape, but what's the difference? Now, comparing the size of everything in this defining equation between m and n1, because m is multiplied by d, our new variable is shorter. So it'll be shorter by something which looks like this, n on d. And now we apply the V bound for summation over m. So this situation of having one variable shorter is not ideal. We want them to be about the same size, and this is due to the limitations of the V bound. When we apply the V bound, our upper bound is only going to depend on the denominator in our sum and not the length. So it's this step where we lose a bit. And the question is, can we do better here? And we can by introducing input from the geometry of numbers. So the basic idea is, if you consider this sum, interpret this as you're summing over lattice points. Now we can choose an almost orthogonal basis for this lattice. And we look what happens when we execute summation over this almost orthogonal basis. Now, if on average the lattice is parameterized by D, L1, and L2, if they don't have small points on average, then our lengths of summation will be much more balanced than this scenario, leading to a quantitative improvement. So before I explain some of the technical aspects of this idea, I'll introduce a more general problem, for which this one is a special case. So I'll recall that a lattice in Z2 is just a subgroup And the determinant of our lattice is the volume of the fundamental region. And I'll let B be a convex body. And finally, I'll take capital lambda to be a set of lattices whose determinant is about the same size for every, whose determinant lies in a dyadic interval for each L in lambda. And then the sums I will consider are as follows. Which I'll denote by S. And we allow a mild dependence of A on our family. And by this I mean its size doesn't grow too much with respect to parameters involved. So before I state what's possible for these sums, I'll define what successive minima are. So I'll fix the convex body, and for I equals 1 and 2, I'll define the ith successive minima of L with respect to B to be the smallest lambda such that if we intersect L with a dilate of our body, then this contains I linearly independent points. Then the theorem is that these sums can be bounded in terms of the parameter Q, which controls the determinants, the volume of our convex set and moments of our successive minima. And yes, there's the dependence in terms of these parameters you can make completely explicit in and it's not too difficult to state, but I won't bother writing down the exact bound for the talk. So before I sketch a proof, I'll make some comments on, for applications to, say, Bedin and Chandy's paper, how do we handle these moments of successive minima? Now for the special case that arise in these bilinear forms with Kloosterman fractions, our lattices are parameterized by some multiplicative properties. Now, since these moments control the average value of the smallest point, if these moments were too large, then too many lattices would contain a small point. And since these lattices are parameterized by equations, we would say certain equations have lots of solutions. And then, as it turns out, we can count solutions to these equations in quite an elementary way. So the proof of this theorem is based on something known as a Mahler basis. You can also think of it as a basis which would be outputted by, say, the LLL algorithm. All right, so I'll state we let L be a lattice and B a convex body. Both in dimension 2 and as in the statement of the theorem. There exists a basis which I'll index by V's of L such that each point in the intersection of L and B has a representation as linear combinations of V1 and V2 such that L1 is bounded in terms of the first successive minima of our lattice, and L2 is bounded in terms of the second successive minima of our lattice. So a basis like this has to be approximately orthogonal, because by Minkowski's second theorem, we know we can approximate the number of points in this lattice, and it's about what you get if you multiply the reciprocals of the successive minima. All right, so let's fix a lattice, and we'll expand this sum in terms of a Mahler basis. So expanding n and m like this, and we substitute into here. So we get something which looks like the following. Now, after a bunch of manipulations with this, say what's sort of the usual sort of manipulations if you're looking at the action of SL2 on these sorts of objects. We get something like this. So now what we'll do is we'll fix the smaller of the two and then sum over the larger of the two variables. And this will bound things in terms of the successive minima, well, the first and the second successive minima. And then using Minkowski's second theorem, you can remove the dependence on the second successive minima at the cost of introducing a term involving the determinant of the lattice, which we're controlling by assumption. So I think I'll stop there. Yeah.